Okay, let's start. And so, as always we do, we need to copy all of these terms in here. And right now, this ECG signal must be applied to the what? To the Fourier transform. Okay? In this case. And also we need to add the sampling frequency in here, the record fs. Okay? First of all, we need to copy all of these terms just like this one. It's the same functions, which is defined in the previous example. ft functions, okay? It's the same structure, and so we can apply easily on the any other data set, okay? So, in order to apply the whole codes, the PLT figure can be built with what the fixed size 12.8 and PLT subplot 2, 1 and 1, okay? And plot time series ECG1 and times and time series data, okay? And after that, the PLT subplot 2, 1, 2 and plot discrete Fourier transform ECG1 and sampling frequency and DFT up to what? The 260 Hertz, okay? And PLT tight layout and PLT show. These are the prepared functions which are defined in the previous example, and so we can apply to the what? The ECG1 signal on this case, okay? And so, just see that if we have the 1 second data for a given ECG signal, and so we have this kind of Fourier transform is included in here, up to what? The 180 Hertz, because to what? 360 Hertz is the R sampling frequency, which means that it's based on the Nyquist criteria, we can obtain the whole signals up to the what? The 180 Hertz, okay? And also, if we increase the what? The 10 seconds signals in here, so see that the whole the components are built within the what? Within up to 50 Hertz, which means that we have a peak, for example, in the what? The 1.2 Hertz in here, and the whole the signal frequencies is given in the what? In the range of the what? The 0 to 40 Hertz for a given this signal. Maybe this is the what? This is the general pattern or the general characteristic features for a given ECG data, okay? So this is the implementation of the what? The discrete Fourier transform on the what? On the biomedical signals, okay? So, number 4, the wavelet visual x.pi examples, okay? So, as always we do, we need to obtain the whole data set in here, just like this one. And so, this is 15 right now, and so we don't need to any annotation in here, and the P signal is obtained. This is 1, and record sampling frequency is obtained in here, okay? And so, how we can apply the Fourier transform or Wavelet transform right now? First of all, the import PyWT library should be added in here. How we can install this? Install Wavelets library, okay? If you want to install this one, and so this zip package is enable us to do what? To apply the any specific wavelet filter on a given data set. Okay? So, first of all, we need to define the wavelet function. Just remember that in the wavelet function, we don't have the Euler identity formula. We can create to the what? To the specific our wavelet convolutional function. One of them is called the dB4. Okay? This is special wavelet function. But you can choose different wavelet pattern in here, and level is equals to the 12, which means that if we have the sampling frequency, for example the 100 or the 1000, and so this 1000 hertz is divided into the what? The 2 over 12 data parts in Turkish. Eğer arkadaşlar bizim 1000 Hz'lik bir sinyalimiz varsa biz bunu 12 bölgeye bölüyoruz. 2 üzeri 12 ile aslında bu kadar frekans, ayrı frekans bölgesine ayırabiliyoruz. Yani 1000 bölü 2 500. 500 bölü 2 250. 250 bölü 2 125. 125 bölü 2 62,5 ... Yani 12 kez biz sampling frekansını bölüyoruz. The sampling frequency is divided up to the what? To the 12 regions in here. Okay? So, first of all, we need to obtain the signal length in here, len ECG1, okay? And coef 1 pi wt wave deck is a specific function to create the what? The wavelet operation, okay? And also coefs 2 for a given ECG2 signal, okay? And so this is the application of the what? Applied this wavelet filter onto what? Onto ECG1 and ECG2 signal, okay? And so the time values is assigned with the what? The MP lin space with the what? 0 to signal length and len coef and endpoint is equals to the false. But for every coef in coefs 1, okay? And times real ECG must also be obtained with what? The MP arrange function, the len ECG1 and D type float, okay? So, how we can visualize the whole the wavelets? For example, the PLT figure, fixed size 12 and 6 is given here, and so PLT subplot 2, 1 and 1, okay? And PLT plot times real ECG and ECG1 and label real ECG1, okay? So, after that, for I and coef must be given in the enumeration of these signals in the coefs 1, okay? And so the PLT plot is assigned with the what? With this one. Time values I, which is given in the what? In the len of coef in here, and so the coef plus I times 2 and the label is equals to the what? F level I, okay? And also PLT title, which is given here, wavelet coef ECG1, okay? And PLT legend and PLT grid on. So, for the second case, we need to create another signals in here, but we don't need to do that. The ECG2 and real ECG2 and coefs 2, time values, level, and coefs 2, okay? And also PLT tight layout and PLT show, okay? And so, if I run this code, and then we will have that one. But firstly we need to give the level 4 in here. Okay, so okay, the real ECG signal is given with what? With the blue one. Okay, but in the level 0 we have different signals. In the level 1 different, level 2 different, level 3 different, level 4 different, which means that we can create to the watt, to the 1 signals, into the watt, into the 5 one, okay, in this case. And so each region has, or each level has a specific rate of the frequency components on the watt on this signal formation, guys, okay. In Turkish, şimdi bakın arkadaşlar, bizim burada bir tane mavi sinyalimiz var. Bu mavi sinyalin içerisinde biz gidip ne yaptık? 4 tane farklı bölgede sinyal çıkardık. Bakın. Çok basit bir şekilde bakın. Bu mavi sinyalin içerisinde şurada bir bakın QRS sinyali var. Gördünüz mü? Şu dik noktalar. Bakın dik noktalar kırmızılara denk gelmiş. Bakın şimdi kırmızı hangisi? Level 4. Level 2. Level 2'ye baktığımızda biz şu dik noktaları bakın level 2'den bulabiliyoruz. If you look at the blue line, which is the real signal, but if you look at the level 2, red line, which means that if we analyze the red line only, and so we can catch the whole the peak line in the blues, which means that this is the high region of the frequency range of these terms. Just like this one, level 3 is equals to what? Is equals to this one. This only created or the contains the high frequency information of these terms. But what about the level 0? In the level 0, we have the low frequency components which is given in here. This is more like to the what? To the R signal. Yani mavi sinyale bakın, en benzeyen sinyal portakal rengi olan. Ama bakın şimdi bu mor renge ya da atıyorum en üstteki o hızlı frekans rengine baksanızda bütün bu mavi piklerin hepsini, mavi aslında pik yapan yerlerin hepsini bakın bulabiliyoruz. Wavelet'in böyle bir avantajı var arkadaşlar. Regional olarak size bu bilgilerin hepsini aslında burada oluşturup verebiliyor. Okay? So, how we can utilize this feature, the frequency feature, in the what? In the artificial intelligence, especially for the convolutional neural network and the neural network structures. We need to, or no, we want to enrich the R dataset in order to what? In order to increase the stability and the classification performance of the neural network, which means that if we enrich the R dataset for a given one signal, and so we can do that. So, number 5, creating dataset example .py can be built with the what? With this one. Okay? And so we can copy all of these terms in here, just like this one. ACG, ACG1, up to 15, and so this is right now maybe assigned to the channel 1, okay? Okay, and so firstly, the signal length is created with what? The LAN channel 1, okay? And so the print PyWT wave list can be given with what? The kind discrete, okay? This represents to the what? The whole wavelet list which is given in here. And so we have to what? LAN we have 106 different wavelet filters, which means that if we have the one signal, and so we can apply the 106 different filters in order to what? In order to create the different characteristics of the R ECG signal in here. Okay? This is a huge advantage. But we don't need to define the whole the wavelets. Just the wavelets can be assigned to the what to this one. For example, the Pytorch 1.1, or we can copy all of these terms in here up to what? Up to this one, for example. We can copy all of these terms, the wavelets in here, just like this one, okay? And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 different filters can be utilized in order to what? In order to increase our diversity of the ECG dataset, okay? And also we can drive the wavelets level is equals to 5, okay? And so ECG dataset can be built with what? The MP zeros. But in these zeros values we need to create the what? To the array or matrices to what? To contain both the real signal and the wavelet outputs. We need to store it, okay? And so we need to give the what? For example, the signal length firstly, okay? This one, and also in this case wavelet level plus 1 times length of wavelets, which means that 11 wavelets, and also wavelets level times 1 signal length is equals to what? The real signals, or contains the real signals and the wavelet signals in a what? In an array or the matrices, okay? And so the print LAN ECG dataset in here. See, 66, okay? So firstly, store the real ECG data in array. But how we can do that? We need to do that in the what? In the normalized version, okay? The channel 1 is equals to the channel 1 minus MP mean channel 1, okay? And also mean value is assigned to mean ECG channel 1, and max value, this is the max, okay? And after that the channel can be normalized with the what? The channel 1 minus mean value divided by max value minus mean value. This creates the what? To ECG signal in the range of what? 0 to 1, okay? So how we can fill the ECG dataset in here? Okay, counter wavelet assignment is assigned to the 0, okay? For I, wavelet can be enumerated in here just like this one for the wavelets, okay? First of all, apply Wavelet Transform in this case, okay? Coefs 1 pi wt times wavedeck, and the channel 1 and the wavelet and the level wavelets level, okay? So after that, to compute the time values for each coefficient level. Time values, MP, length space, 0, signal length, LAN, coef, just the remember, and so the endpoint, false, and also the type is equals to the int, okay? For coef, in coefs 1, okay? So the print of the LAN times value, or we don't need to do that right now. This is a control checkpoint, but we don't need. For J, coef in enumerate of the what? The coefs 1 So the coef is equals to coef minus MP mean coef. Okay, this is the normalization techniques for the what, but this must be copied, all of these terms in here, but right now for the coef. Okay, it's the coef, coef, and also we need to copy all of these terms in here, but right now this must be coef. This is the normalization values of these terms, and so the ECG dataset can be filled with what the counter wavelet assignments and time values j. Okay, which is equals to coef, and this must be increased with what? With the 1 at each case. Okay, so at each level we fill the ECG dataset just like this one, but how we can visualize it in here right now? For example, visualization of wavelet pictures can be built with what the step size is equals to 500, iteration number is equals to 20, and image number should be assigned in here int signal length divided by step size. This is the window size, okay, for creating to the what ECG patterns. And so this one-dimensional signal is converted into the what? Into the 2D one with the help of the wavelets. Okay, so CMap is where it is. It's the basic tool for the what, for plotting the whole the numbers in here. And so for I in range of 0 to signal length minus step size and iteration number in here, and so the new matrix is assigned to the what? MP zeros. And so first of all the D type, this must be assigned to the float, and also we need to give the tuple values in here, the iteration number, and also we need to give the wavelet levels plus 1. Plus 1 is coming from to the what? To the real signal. Okay, and so the LAN wavelets. Okay, this is a new matrix, but it's empty. And after that the new matrix is filled with the what? With the 255 ECG data set of the what? The total elements of the what? The I to I plus iteration number, which means that at each iteration this is the windows of the what? 20, and so 20 number is included into the what? Into the these values of the new matrix, and so we can iterate or the window create the windows in order to what? In order to visualize our algorithm in here. And after that the counter is the counter plus 1 and PLT figure fixed size 8 and 8 and PLT im show can be called in here new matrix, and CMap is equals to the CMap. Okay, so PLT tight layout and PLT show must be written in here. And so if I run this code, see we have 20 data in here, but we have the 66 values which is given in here just like this one. In the first place, in the first level we have the real ECG signal, but the other ones are created with the wavelet patterns in here. First of all, in the second place this one, in the third place this one, in the fourth place, fifth place, sixth place, seventh place. See, we can create a 2D dimensional data based on this information by using the wavelet transformation. So this is huge enrichment to the classification of the ECG signal, or the any biomedical signal, or the any control signal, or the any measurement signals in here. These have the many features based on the frequency patterns of these terms, guys. Okay. So in Turkish. Şimdi arkadaşlar bakın. İngilizcesini anlattım. Burada bizim kullanabileceğimiz bir sürü wavelet kalıbı var. Bu wavelet kalıpların hepsi aslında ne yapıyor biliyor musunuz? Aynı bizim bu FFT ya da atıyorum işte Fourier Transform ya da Short Time Fourier Transform gibi aslında filtre uyguluyor. Ama o filtrelerin bir güzelliği var. Bunların hepsi birbirinden farklı. Yani ben Bior 1.1 ile 1.3 uyguladığımda farklı sinyaller alıyorum arkadaşlar. Resimleri farklı oluyor. Bunlar da benim veri setimi genişletmeme sebebiyet veriyor. Bakın wavelet level var ya burada. 5 mesela yazıyor burada. Burada 11 tane sayı var. 11, 5. O zaman 11 tane varsa burada ben 5 level'a bölüyorsam bunu 11 çarpı 6 ile aslında 66 tane farklı kalıp elde ediyorum. Sadece bir tane sinyalden. Ve bunların da hepsini gidiyorum ne yapıyorum? Normalize edip buraya koyuyorum. Ve hepsini bir tane iteration number diyor ya 20 adım 20 adım atarak aslında bu sinyalin içerisinde çıkarabiliyorum. Yani ben buraya bakın 2 yaparsam bakın şimdi 30 tane sinyal oldu. Ama bakın resim artık buna döndü. Yani benim bir tane EKG sinyalim artık 32 tane komponentten oluşan bir sinyal oluşturdu. Eğer ki bakın ben bunu 2 yaptım ya. Gittim buraya iteration number'a gidiyorum. Sallıyorum burada 200 olsun. Şimdi bakın 200 olunca da 200 tane yan yana veriyi aslında 0'dan 200'e kadar bütün sinyalin aslında hepsinin içindeki değerleri burada bana çıkarabiliyor arkadaşlar. Aynı şekilde gittim. Tekrardan bunu 5 yaptım mesela. Yani ben bir tane sinyalden arkadaşlar böyle bir resim oluşturuyorum. Bakın bunlar QRS sinyalleri görüyor musunuz? Yani direkt aslında bu resmin içerisinden ben öyle bir kalıp oluşturuyorum ki farklı aslında formda farklı verilerin hepsini en güzel bir şekilde generate edebiliyorum. Yani aslında o kadar çok veri çıkarabiliyorum ki bundan farklı olarak. Benim yapay zekam artık çalışmak zorunda kalıyor. O kadar iyi klasifiye ediyor ki, o kadar iyi sınıflıyor ki ben bunu kullandığımda her şeyi çözebilecek hale geliyorum arkadaşlar. Bu bizim için çok önemli. Çünkü siz mesela bir uygulama yapacaksanız kesinlikle ön işleme yapmak zorundasınız. Ön işlemede de böyle işlemler yapmadan eğer işlemleri çözmeye çalışırsanız kesinlikle sizin algoritmanız doğru ve iyi bir şekilde çalışmayacak arkadaşlar. Yapay zeka uygulamalarında özellikle. O yüzden benim bunu size göstermem önemliydi. Sorunuz var mı?